Hello and welcome. My name is Amar. This is the first episode of Build a Database from Scratch. I'm going to assume you know nothing at all about databases. Not what a table is, not what a query is, nothing. By the end of this video, you will be able to create a database, put real data into it, and ask it questions. You will write those questions yourself. Everything you see me type here is real, and it is running on a real database server. Nothing is faked, and nothing is sped up except my typing. Here is what we will cover: what a database actually is, and the picture you should keep in your head, how to make a table, and how to put rows into it, how to ask questions and how to filter and sort the answers, how to make the database count things and work out averages, how to connect two tables together, and the two mistakes that catch almost every beginner. One more thing before we start. I will stop several times and ask you to answer before I do. Please actually answer out loud if you can. Trying to remember something is what makes it stick. Watching me do it is not. So, what is a database? You have almost certainly seen one already without knowing it. Think of a spreadsheet. It has columns across the top like name and score. And it has rows going down, one row for each student. That grid is called a table, and a database is a collection of tables. That is genuinely most of it. So why not just use a spreadsheet? Because of one thing: asking questions. In a spreadsheet, you find things by looking, or by scrolling, or by clicking a filter. In a database, you write the question down as a sentence. And the language you write it in is called SQL. Now here is the picture I want you to keep for the whole video. A table is a grid of rows. A question is a sieve. Every row in the table goes into the top of the sieve. Some rows fall through and come back to you, the rest do not. That is it. Rows go in, rows come out. Hold on to that because it explains almost everything that confuses people later. And here's the part that surprises everybody. You never tell the database how to find anything. You do not say, start at the top, look at each row, compare the score. You say what you want, and the database works out how. If you have written any code before, that will feel wrong. It is the single biggest idea here. Let us make a table. I am at a real PostgreSQL server running in a container on this machine. PostgreSQL is one of the most widely used databases in the world, and it is free. This little prompt is where I type. Before a table can hold anything, we have to describe its shape. What columns does it have, and what kind of thing goes in each one? Watch. Create table, then the name I am giving it. Students. Then a bracket, and inside the bracket, one line per column. ID and the word int. Int is short for integer. A whole number. Name. And the word text. Text is any run of characters. Score, another whole number, and class ID, which will matter later on. Then a closing bracket and a semicolon. The semicolon means I have finished, go and do it. Forgetting it is the most common thing that happens to beginners, and the prompt will just sit there waiting. So, what do you think comes back? The database says create table and nothing else. That is not the database being unhelpful. It is telling you it did exactly what you asked, and there is nothing to report. You will see that a lot. Silence is success. Notice what we have and have not done. We have described a shape, 4 columns, And what goes in each? There is not one single student in there yet. So let us put some in. The word for adding a row is insert. Insert into students' values and then the rows. Each row goes in its own set of brackets, and the values inside have to come in the same order as the columns we just declared. ID first, then name, then score, then class ID. Look at the names, they are wrapped in single quote marks. Text always is, the numbers are not. That is how the database can tell the difference between a piece of text and a number. 5 students, 5 sets of brackets separated by commas, and a semicolon at the end to send it. Insert 05. The 5 is the part that matters. 5 rows went in. The 0 is an old PostgreSQL detail you can safely ignore for now. Now the interesting half, getting data back out. The word is select, and this is the one you will type most often for the rest of your life. Select star from students, semicolon. Let me take that apart word by word because every piece is doing a job. Select means give me back some columns. The star means all of them. Every column. From students says which table to take them from. And there is no filter, so every row comes back. So before I run it, tell me how many rows should come back. 5, because we put 5 in. And there they are. Look at the shape of that answer for a second. The database drew you a little table. Column names across the top, then a line, then 1 row per student. And at the bottom, it tells you how many rows it found. That bottom line is worth reading every single time. When a query goes wrong, it is very often that number that tells you. Beside the terminal, I am drawing the same 5 rows as bars. The longer the bar, the higher the score. The table and the picture are the same 5 rows. I am not going to keep saying that. Now, we asked for every column, but we rarely want every column. Instead of the star, you can name the ones you want. Select name, score from students. Same 5 rows, 2 columns instead of 4. That is the first real lesson about select. The star chooses columns. It has nothing to do with rows at all. Which brings us to rows and to the sieve. To choose rows, you add a where clause. Here is the same query with 1 extra line, where score is greater than or equal to 80. Stop the video for a second if you need to and answer this. Look at the bars. How many students score 80 or more? 3 of them. And 3 rows come back. Watch what happened in the picture. 2 bars faded out, 3 turned green. The faded ones were not deleted. They are still in the table. They simply did not fall through the sieve. That distinction matters more than almost anything else in this video. A query never changes your data. It only chooses what to show you. Let me do that by hand, 1 row at a time, because this is the whole idea in one place. Row 1. The score is 91. Is that 80 or more? Yes, so it goes through. Row 2, the score is 68. Is that 80 or more? No, so it stays behind. Row 3, the score is 84. That is a yes. Row 4, the score is 77. That is a no. Row 5, the score is 95. Another yes. 3 yeses, so 3 rows. The database asked that question once per row, and it asked it about every single row. It did not skip ahead, and it did not know any of the answers in advance. Hold on to that, because in the last section we catch it doing exactly this and see why it becomes a problem. Now the comparison itself, Greater than or equal to is written as two symbols greater than, then equals. You also have plain greater than, less than, and equals. And here is something that trips up anyone who has programmed before. Equals is one equals sign, not two. In most programming languages, a single equals sign means assignment, and a double one means comparison. In SQL, there is no assignment here, so one sign is all you need. The rows came back in no particular order. Actually, in the order they happen to be stored, which is not something you should ever rely on. If you want an order, you have to ask for one. We add an order by clause on the score. That last word is short for descending, highest first. Leave it off and you get ascending, lowest first. Same 3 students. Now in the order I asked for one more clause, and it is a useful one. Limit 3. Give me the first 3 rows and stop. Put those two together, order by and limit, and you have written a top 3. Notice I dropped the where clause for this one. This is every student, sorted, cut off at 3. That is a real pattern you will use constantly: highest scores, newest orders, most recent messages. Everything so far has handed you rows. Sometimes you do not want rows, you want a single number about them. How many students are there? Select count star from students. Count star means how many rows fell through the sieve. 6. No. 5. We have not added anyone else yet. And 5 is what comes back. Look carefully at the shape of that answer though. It is still a table, 1 column, 1 row. The database always answers with a table, even when the answer is a single number. Count is one of a small family called aggregate functions. An aggregate takes many rows and squeezes them into one value. Here are 3 more in one query: min score, max score, and the average rounded to 1 decimal place. Before it runs, the lowest is 68 and the highest is 95. What do you think the average is, roughly? 83. And on the picture, that is the line straight through the middle. That is why the picture is there. A single number means very little on its own. 83 only means something when you can see all 5 bars around it. One last thing about that query. The word as average just renames the column in the answer. It changes nothing about the data, it only makes the output readable. Right? First recall, I am going to clear the screen. Without looking, say the query that gives you every student who scored 80 or more. Take your time, say the whole thing. Select name, score from students, where score is greater than or equal to 80. If you got the select and the from and forgot the where, that is completely normal. The point was the attempt, not the score. Now let us make things realistic. Real databases almost never have one table. Look back at our students. There is a column we have been ignoring. Class ID, every student has a 1 or a 2 in it. A 1 or a 2 is not very useful to a human. So let us make a second table that says what they mean. Create table classes with an ID and a name. And 2 rows, 1 is mathematics, 2 is physics. Now why did we do it this way? Why not just write the word mathematics into every student row? 2 reasons, and they are the reasons. Databases are built like this. First, if you spell it wrong in one row, you now have 2 different subjects. Second, If the class is renamed, you change it in one place instead of hunting through every student. The number is a reference. It points at a row in the other table. And the word for gluing the two together is join. Here it is, and this is the longest query so far. We will go slowly. Select s.name and c.name from students S. That letter S is a nickname. It just saves typing the word students over and over. Join classes c on s.class.id equals c.id. That last part is the whole join. Everything else is decoration. It says a student row and a class row belong together when the student's class ID matches the class's ID. So what should come back? Five rows, one per student with the subject spelled out. And that is what we get. The number 2 has become the word physics, and it was never stored on the student at all. One warning about join, because it is quiet and it bites. Suppose a student had a class ID of 3. There is no class 3, we only made 1 and 2. What do you think happens to that student? They vanish from the answer completely. Not an error, not a blank, they are simply not in the list. A plain join only keeps rows that found a partner on both sides. So if a join returns fewer rows than you expected, that is almost always why. There is another kind called a left join that keeps them and leaves the other side blank. You do not need it today. You do need to know your rows can disappear. Now we can combine the two ideas, and this is where SQL starts to feel powerful. We can count and we can join. What if we count per class? The word is group by. Group by takes all your rows and puts them into piles. One pile per class. And then it runs the aggregate separately on each pile. So instead of one average for everybody, you get one average per class. Here is the query. It is the join we just wrote with two changes. We added count star and the average to the select. And we added group by class name at the bottom. Predict before I run it. Mathematics has 3 students. Physics has 2. Which class do you think has the higher average? Mathematics at 90. Physics at 72.5. 2 rows. Because there were 2 piles. That is the rule for group by. And it is worth saying plainly. You get 1 row out per pile, not 1 row per student. This is the moment SQL stops being a way to look things up. One sentence just joined 2 tables, sorted every row into piles, counted each pile and averaged it. In a spreadsheet that is a morning of work. Before we change any data, one thing that took me years to learn, and it is short. You write a query in one order. The database reads it in a completely different one. You write select first. The database does select almost last. Here is the real order. From first. Which table are we even talking about? Join next. Glue the second table on. Where next. Throw away the rows we do not want. Group by. After that, put whatever survived into piles. Select. Now, choose the columns and run the aggregates. Order by sort what came out. And limit, last of all, cut the list short. Why does that matter to you today? Because it explains an error you are guaranteed to hit in your first week. Remember, we renamed a column to average using the word as if you try to use that new name inside a where clause, the database refuses and says it does not exist. And now you can explain why where runs before select. So at that moment, the name has not been created yet. It is not the database being difficult. You asked for something that had not happened yet. So far, we have only read, let us change something. The word is update. Update students set score equals 88, where name is Bruno Kovacs. Notice the two halves. Set says what to change. Where says which rows to change it on. Update 1, one row changed. And if we look him up, the score is now 88. Now I want to stop and give you the most important warning in this video. The where clause on an update is not optional in practice. It is optional to the database, and that is the danger. If you leave the where clause off, the database does not ask if you are sure. It sets every single row to that value, all of them. The same is true of delete. Delete from students where name is something removes one student. Delete from students with no where clause empties the table. There is a habit that prevents this, and professionals really do use it. Write the query as a select first. Look at the rows that come back and make sure they are the ones you meant. Only then change the word select to update or delete. You will not regret building that habit early. One more idea, and it is the one that catches everybody. What happens when you do not know a value? Let us add a 6th student whose score has not been recorded yet. Where the score should be, I write null. Null does not mean 0. 0 is a score. It means the student sat the exam and got nothing. Null means we do not know. The box is empty. Now watch what that does. Here are two counts in one query, count star and count score. Predict, will those two numbers be the same? 6 and 5. Count star counts rows, there are 6 rows. Count score counts values that are actually there. There are 5. Nulls are skipped quietly, and the average skips them too. And now the trap itself. It seems obvious that to find the empty one, you write where score equals null. Predict what that returns. 0 rows. Not an error, not a warning. 0 rows, as if the student did not exist. Here is why, and it is actually logical. Null means unknown. So asking is this unknown value equal to that unknown value has no sensible answer. The database does not answer yes or no. It answers I do not know. And a row only comes back when the answer is a definite yes. The correct way is different wording, where score is null, not equals null. And there he is. Look at the score column in that answer. It is not 0, it is blank. Last one. And this is a look ahead. We have been asking the database to find things, and it has been finding them instantly. But how is it doing it? There is a word that shows you, and it is called explain. Put explain in front of any query, and the database tells you its plan instead of running it. Read the first line of that answer. It says it is doing a sequential scan. That word sequential is the one that matters. It is telling you to find the student with ID 4. I am going to read every row from the top and check each one. With 6 students, that is instant. With 6 million, that is the difference between a page that loads and a page that does not. The fix is called an index, and it is what the next episode is about. We are going to open the file the database keeps on disk and build one ourselves. Before you go, we are going to rebuild the whole language from an empty screen. This part is the reason you will still remember this tomorrow. Answer each one out loud before I say it. 1. What word makes a new table? Create table. 2. What word puts a row in? Insert into. 3. What word reads rows back? Select. 4. Which clause chooses rows? Where? 5. Which clause sorts them? Order by. 6. Which clause makes piles and counts each one? Group by. 7. And this is the one that matters most. How do you find rows with no value? Is null never equals null? If you got 5 of those 7, you can genuinely use a database now. Here is your exercise, and please do it. It takes 10 minutes. Write one query that gives you the average score per class, but only counting students who scored 80 or more. Everything you need is in this video. You will need a join, a where clause, and a group by. The answer is in the description, but try it first. Next episode, we stop using a database and start building one. We are going to open a real file, look at the actual bytes, and find a record without searching for it. That sequential scan we just saw is the problem we will fix. Thank you for watching, and I will see you in the next one.